Hello, everyone. We continue with this lecture on the topic of determinants, and another way to find the value of the determinant of a square matrix is through elementary row operations. Let's recap what we have in lecture 9 on determinant of a square matrix. Right? So in lecture 9, we learned that you can use a formula to calculate the determinant of a 2 by 2 matrix. If you have a higher dimensions, for example, 3 by 3 matrix or 4 by 4 matrix, you can do the calculations on the minors and then the cofactors and then combine them in a way that the determinant of a matrix is equal to the sum of the entries multiplied with their corresponding cofactor. Okay, so that's how you find the determinant. Also, there's another way to calculate the determinant of triangular matrix, right? So we have three types of triangular matrix: diagonal matrix, upper triangular matrix, and lower triangular matrix. And the determinant of those matrices is equal to the product of the entries on the main diagonal of the matrix. And in this lecture, we also talk about determinants and pair that with elementary row operations. Again, there are three basic elementary row operations that you can perform on a matrix. The first one is to interchange two rows, and the second one is to multiply a row by a non-zero constant. The third operation is to add or combine. So let's you add multiple of one row with another row, right? And we're going to see the effect of those elementary row operations on how you can obtain the determinant of the matrix. All right, so that's the learning objective, right? Use elementary row operations to evaluate a determinant. Then later on, we will write down some conditions that help us recognize a matrix that produce a zero determinants. All right, so let's start with the simple matrix of the form 1, 4, 2, -3. And let's calculate the determinant of this matrix. All right, so the determinant of A is going to be determinant of 1, 4, 2, -3. So 1 times -3 minus 2 times 4. This gives me -11. So that is the determinant that for matrix A. Now, if given this matrix A, you interchange two row of A, you obtain a new matrix, right? So let's say B is obtained from A by interchange two rows. Right? So 2, -3, 1, 4. Right. So you obtain a new matrix. And the determinant of this matrix is, right, so this notation indicates that I want to find the determinant of the matrix B. It looks like an absolute value, right? But in this particular context, this is the determinant of B, right? So it's equal to the determinant of the matrix 2, -3, 1, 4. Right, this is equal to 2 times 4 minus 1 times -3, or this is equal to +11. So you notice, even though that is just one example, you may notice that the determinant of B of this new matrix is the opposite or equal to the opposite of the determinant of A. Right. So that's one notice that we see for elementary row operation and the determinant. And we write down a more formal definition for that later on. Now, moving on to the next example, you want to add a multiple of a row to another row. Right. So the matrix B is obtained from A by adding, let's say, -2 times the first row of A to the second row of A. right, so let's start with A. The matrix A is of the form 1, 4, 2, -3. Now, what we do to get B is that you're going to multiply the first row by -2 and then add with the second row. Right, so similar to the Gauss-Jordan eliminations method that we did, in this case, row 1, we just borrow row 1 and we make the change in row 2. So you have -2 times row 1 plus row 2 to produce a new row 2. And the new matrix we obtain going to be, so 1, 4, row, first row remain the same. And the second rows become, so -2 times 1 is -2, added with 2 becomes 0. Then -2 times 4 is -8, added with -3 is -11. Now this is matrix B. Now you want to find the determinant of the matrix B, right? Or the determinant of 1, 4, 0, -1, 11. And this is the triangular matrix, right? So that the determinant is just the product of the entries on the main diagonal, but just basically use the formula of the 2 by 2 determinant, and you get this is equal to -11 as well. So by adding a multiple of a row to another row, you see that the determinant of the new matrix is equal to the determinant of the original matrix. So that's another notice that we have for elementary row operations. Okay. Now for the last elementary row operations, that we're going to multiply a constant to a row, right? So the matrix B is obtained from A by multiplying the first row of A by 1/2. So what do we get? So here the matrix A, the original matrix, 1, 4, 2, -3. So you multiply the first row by 1/2. So 1/2 row 1 will give you a new row 1. So in this case, row 2 remains the same. So 2, -3. So 1/2 times 1 give me 1/2. And 1/2 times +4 is going to be +2. And this is the matrix B. So the determinant of matrix B is equal to 1/2 to -3, or this is equal to 1/2 times -3 minus 2 times 2, or -3/2 minus 4 equal to -11/2. So for this particular case, what we notice is that when you multiply the first row or the second row, or any row for that matter, of the given matrix by a constant, non-zero constant, you obtain a new matrix. The determinant of this new matrix is equal to that constant that you multiply times the determinant of the original matrix. So that the three notice that we have. All right, so first, when you interchange two rows, the determinant of the new matrix equal to the negative of the original matrix, the determinant of the original matrix. When you add in a multiple of a row to another row, then the determinant of the new matrix equal to the determinant of the original matrix. And when you multiply a non-zero constant to a row in a regional matrix, the determinant of the new matrix is equal to that constant multiplied with the determinant of the original matrix. Right? So that's is the theorem that we need to put in. So let's say you have two matrices, two square matrices. So when B is obtained from A by interchanging two rows of A, we get that the determinant of B is equal to negative of the determinant of A. And for the second case, when B is obtained from A by adding a multiple of a row of A to another row of A, we get that the determinant of B is equivalent to or equal to the determinant of the original matrix. And in the last case, when B is obtained from A by multiplying a non-zero constant to a row of A. So that non-zero constant C, let's say we call that C, then the determinant of B is equal to C times the determinant of A, right? So there are three cases for three different elementary row operations. So now let's find the determinant of the following matrix. Right, you can use the formula in that we learned in lecture 9. This is just another way to obtain the determinant of a matrix. Okay. So obviously, if you use the procedure that we did in lecture 9, it's very simple that you can just choose the first column to work with because the first column contains 2 zeros. But again, what we want to experience is the change in the elementary row operations to see what happened to the determinant of the matrix. All right, so finding the determinant of this matrix, so 0, -7, 14, 1, 2, -2, 0, 3, -8. Right. What we do first is to interchange two rows, right? Interchange row 1 and row 2 and see what happened. So when you interchange row 1 and row 2, you get 1, 2, -2, 0, -7, 14. Row 3 remains the same, 0, 3, -8. Now you go back to the calculations, to the theorem here. When you interchange two row, right, the determinant is equal to the determinant of B equal to negative of the determinant of A. But be careful here in the setup. What we're looking for is the determinant of the original matrix, right? You want to find the determinant of A. So that means, let me rewrite this a little bit. So the determinant of B, of A is equal to negative of the determinant of B, right? So you put in the negative sign here. Okay, that's fair enough, right? Now, let me quickly note here that we interchange two row. Change row 1 and row 2, so that's what we did. Now, in the next step, what we want to see is to multiply the second row by -17. In other words, we factor the value 7, oh sorry, -7 in the second row, right? So you have negative still in front of the determinant. I multiply with -7 because you want to factor 7 out of the second row. So 1, 2, -2, 0, 1, -2, and 0, 3, -A. Now, you may wonder, why is that the case? We haven't talked about factor yet. We only talk about multiplied or adding a multiplying a non-zero constant to a row of A, right? What you want again to do is to, right, multiply the second row by -1/7, right? Okay, so bear with me here. So you multiply by -1/7. So the determinant of B is equal to -1/7 of the determinant of A. But again, what are you looking for? You're looking for the determinant of A, the determinant of the original function. So therefore, you have to rewrite this equation so that you get the determinant of A is equal to -7 times the determinant of B. So in other words, instead of multiplying a non-zero constant to a row of A, you factor the number from the row out of the determinant. That's what we did over here, so that it can reflect this change or this manipulations. Okay, so instead of saying that, okay, can I multiply the second row by -217? I can also say that I factor in -7 out of the row of out of the second row of the determinant. So that's why you get -7 and not -1/7. Now, the last thing that we're going to do is to add -3 times the second row to the third row to produce a new third row. Right. So this give me, so negative with -7 is +7, right? So when you adding a multiple of a row of A to another row of A, then the determinant of the new matrix equal to the determinant of the original matrix. So there's nothing change in the determinant. It's just that the calculations will be. So I'm gonna have the change in the third row. So again, what we do is to add -3 times the second row to the third row to produce a new third row. So -3 times 0 added with 0 becomes 0. So now -3 times 1 is -3, add this with 3 becomes 0 as well. -3 times -2 is +6. Added with -8 become -2. Even though we do this adding a multiple of a row to another row, there's nothing change in the determinant. Okay, so 7 you have in front is going to be equal to 7 times. Remember, this is now become a triangular matrix, right? So the determinant is just the product of the entry on the main diagonal. So 7 times 1 times 1 times -2 is equal to -14. All right, so it looks a little bit more complicated than what we did in the last lecture, but it's give you another way to actually observe how to obtain the determinant of a matrix under elementary row operations. Okay. So moving on to the last topic in this lecture, that you consider matrices and the zero determinant of those matrices. Right? There are three conditions that yield a determinant of 0. Right? So the first, so let's consider A is a square matrix, and then any of the following conditions below is true, right? Then the determinant is equal to 0. So the first condition is that an entire row or even so or an entire column consists of 0. So let me quickly write down an example here. So you have a matrix of the form 0, 0, 0, 2, 4, -5, 3, -5, 2. So without doing any calculation, I recognize that the first row consists of all zeros. So the determinant of this matrix is going to be equal to 0. So quick note here, the first row has all 0. Now, the second conditions that we can consider is that 2 rows or columns are equal. Right. So you can see in the next example here, you have the following matrix or determinant: 1, -2, 4, 0, 1, 2, 1, -2, 4. So the first row and the second row are the same. Therefore, you can say that the determinant is equal to 0. Right? The first and third rows are equal. And the last conditions that one row or column is a multiple of another row or column. Right, so for example, we have the following determinant to calculate: that 1, 2, -3, 2, -1, -6, -2, 0, and 6. So this particular determinant is also equal to 0, because if you notice that, so let me say this is the first column, the second column, and the third column. So the third column is equal to -3 times the first column, right? So one column is the multiple of another column. So in this same case, we know that the third column is a multiple of the first column. All right, so again, the three conditions, when you see either of these conditions, then determinant of the matrix is going to be equal to 0. All right, so the first condition is that the entire row is going, or column, consists of 0 entries. So automatically, you can say that the determinant is equal to 0. If you have 2 rows or columns are equal, the determinant of the matrix also equal to 0. And the last condition is that one row or column is a multiple of another row or column. Okay, so let's move on to the following example. Right. So let's try to find the determinant of this following matrix: 1, 4, 1, 2, -1, 0, and 0, 18, and 4. And again, you of course can use the technique that we learned so far to obtain the determinant of this matrix, right? But I want to again use this opportunity to reflect on what we just learned on the 0 entries of the matrix. Oh, sorry, the determinant equal to 0 of this particular matrix. All right, so what do we do here? So you want to find the determinant of matrix A, or the determinant of 1, 4, 1, 2, -1, 0, 0, 18, and 4. All right, so what we do now is to add -2 times the first row to the second row. And we produce, right? So 1, 4, 1. You just borrow row 1 in this case. Right. And the third row remained the same. And now the second row has become, so -2 times 1 is -2 added with 2 becomes 0. -2 times 4 times 4 is -8 added with -1 becomes -9. And -2 times 1 is -2 added with 0 is -2. And you notice between these two rows, row 1 and row 2 and row 3, that the second row and the third row are multiple of one another. All right, so therefore the determinant of A is going to be equal to 0. All right. So that's it for me for this lecture. Again, in this lecture, we'll look at another way to or we look at the effect of elementary row operations on the determinant of a matrix, right? So elementary row operations, there are three types, or there are three basic row operations: interchanging two rows, adding a multiple of a row to another row, and multiply a constant to a row in a matrix, right? Depends on the situations. You have different conditions for determinant of to calculate the determinant of the new matrix after performing the row operations on the original matrix. And toward the end, we look at the matrices and the zero determinants. There are three different conditions that we can look at when you want to see if the determinant of a matrix is equal to 0 or not. If either of these three conditions satisfied, then the determinant of A is equal to 0. The first condition is that an entire row or an entire column consists of 0. Right? The second condition is that two rows or columns are equal. And the last condition is that one row or column is a multiple of another row or column. That's what we see in the example that we just did right here. Okay. So that's it for me. Please let me know if you have any questions. Thank you.